The title of my talk today is Deep Learning to Smile, Neural SDEs. And as I'm working in mathematical finance, you might already guess that I'm going to talk about volatility smiles and how to learn them using neural SDEs. I'm currently affiliated with Unica Insurance Group and Vienna University of Economics and Business, and I gratefully received funding within the Post-DocTrack program of the Austrian Academy of Sciences. This talk today is based on joint work with Krista Cucchiaro and Kevin Court. So what is the motivation to use neural SDEs? And I will come to a precise definition of what I mean with neural SDEs in a second. But what you can think about is a classical Ito SDE, where the coefficients are parameterized using neural networks. So in classical calibration, what one typically does is that you choose one model from a pool of asset pricing models, given current market and historical data. So traditionally, this is done using Monte Carlo techniques, but this is oftentimes quite computationally intensive, especially if you think about Bayesian calibration procedures. And oftentimes, if you do not use Bayesian calibration, then what you get is typically point estimates only. So there was a new model class introduced, so-called neural SDEs, and they leverage on neural networks to model the SDE coefficients. The great thing about them is that you are still within the realm of classical math finance as you're working with SDEs, but you gain this additional flexibility coming from parameterizing your coefficient as a neural network. And as you might guess, so you can approximate the SDE coefficients on compacts due to classical universal approximation results by Zibenko and Hornig, for example. But the question is, can we also approximate or can we say something about the approximation of the solution of the SDE? So here one has to work a little bit, and there were recent advances for the approximation of SDE solutions in an L2 sense by Tao and co-authors and Kosik and co-authors. And in this talk, I present a new result that combines techniques from Kosik and Tao with quantitative bounds from Barron, 1993. So we can explicitly express the approximation error in types of the number of neurons of your neural network architecture, which is a quite interesting result. So what is the model that I consider? We consider a capital time horizon T and a constant interest rate R, and we are working on a probability space with WT1 being a standard Brownian motion supported on this space. We consider the following parametric SDE, xt theta, consisting of two components, st theta and vt theta, where here st theta stands for the dynamics of the asset price process and vt theta, the spot variance process. The two are driven by WT1, a standard Brownian motion, as I told you, and WT2, a correlated Brownian motion with correlation constant ρ. Here, you see that the diffusion coefficient of the asset price process depends on T, st theta, and vt theta. So this is a quite general framework which can also incorporate local stochastic volatility models. So in the case where we consider sigma BV and sigma V to be neural networks, we call the system a system of neural SDEs. The model is free of arbitrage by construction, as the discounted asset price process is a local martingale. So existence and uniqueness hold under standard assumptions and considering sigmoidal activations. As I told you, the goal is to approximate the solution of a classical Ito SDE, which I now call XT, with a neural SDE xt theta p, where theta p shall denote that I consider a shallow neural networks with parameters theta and p neurons. So to be in line with the neural SDE we just considered, we look at the non-neural counterpart, the xt here, and this is driven by a two-dimensional correlated Brownian motion again. And here, B and sigma x denote the drift and diffusion components respectively. Also here, we assume that the usual assumptions such that a unique strong solution exists are satisfied. We would now like to derive an estimation error between the solution of 5 and the neural SDE I showed you a second ago. And to do this, we have to introduce functions that lie in the so-called Barron class. So here we have to get this quantitative error bound to have some additional assumptions, and they have to do with the Fourier transform of the neural SDE coefficients that we consider. So we have a constant capital C, and we denote by gamma C the set of functions for which the following conditions hold. F admits a Fourier representation of the following form. Here tilde F is the Fourier transform of F. And we have to assume that W F tilde is integrable and that we have some boundedness on W F given by this constant C that we introduced above. I already spoiled that we are going to consider shallow neural networks with sigmoidal activation. And here I define what I mean with a shallow neural network. So you have one hidden layer, activation function phi of the following form, and we have p nodes. Under these conditions, we can state the following universal approximation theorem. So here we have BR, the ball of radius r on Euclidean space. B and sigma x are the coefficients of the non-neural SDE I just showed you, WT, the two-dimensional Brownian motion. And if we have local Lipschitz assumptions, linear growth assumptions, and this Barron class assumption that I just introduced, then I would like you to look at the final result first. We can approximate the solution of x by xt theta p in the following L2 sense. And so what you can see that this expectation is less than or equal to epsilon in our result. And now let us look at the difficult part, or the insight, if you like. It's not difficult, it's only that the notation gets a little heavy. So epsilon, as you can see, is related to the quantities here above. And so this r squared, we recall, is the radius of this ball. Then we have a dependence on k, where k in turn depends on the activation bound, L, C, and T. So they come from the linear growth assumption, the Barron class assumption, and the capital time horizon. And then this P, so this is really the number of neurons that we consider, has to be larger than or equal to this expression, and this in turn depends again on R, C, capital T, and the two Lipschitz constants. Yeah, so this is an interesting result, as it is really a quantitative result. It's a global result, not only for stopping times, and you can express the estimation error really in terms of the neural network architecture. So enough of the theoretical part of neural SDEs. Now I would like to show you some numerical and empirical results. So first of all, we consider a rough Bergomi model setup introduced by Bayer and al. This is the model of the following dynamics. So ST here again stands for the asset price process. And here VT now depends on this fractional kernel YAT, where the fractional kernel looks as follows. Yeah, so you have this parameter A. This is very important in rough volatility models, as it determines the roughness of the model. The fractional dynamics here are very tricky as they are non-Markovian. But what we saw in our experiments is that if you would like to calibrate a neural SDE to a volatility surface that comes from such a rough model, actually the model, so the neural SDE, is able to replicate such a volatility surface, even though the neural SDE itself is non-Markovian. So what we argue is that the neural SDE learns the Markovian projection. So this was introduced by Gyongyi, and there were papers later on by Larson and Long, Bourget and co-authors. And in this context, I would also like to mention the work done by Bruno Dupieux. Of one specific setting, we consider 5,000 Monte Carlo paths. Training does not take too long here. And in our paper, if you would like to look that up, we consider a Bayesian calibration algorithm. So the advantage here is that you have regularization on the one hand, and then you also get some error bounds on the calibrated volatility surface. And this is what I show you here. So here the dashed lines correspond to the 10 and 90% quantile of the posterior draws. So we have a burn-in phase. After that, we consider draws from the posterior, and then I look at 10 and 90% quantiles. This is what you see here. We also have results for the Heston model. And in the Heston model here, what we aim to do is to consider joint calibration under P and Q. This necessitates a change of measure for neural SDEs. And if you are interested in that, you can take a look at our paper again. There are all the details. What is also nice is that we considered exotic options in this calibration as well. And due to the Bayesian algorithm, you get error bounds for the price of this exotic option as well. They are not included in the optimization. They're just, so the price bounds emerge naturally from our Bayesian scheme. This is the implied volatility surface, again with error bounds. Here, what we see is, so we consider two specific time points of the neural SDE. And we consider histogram and QQ plots of the paths generated by this neural SDE that was trained to paths coming from a Heston model. And here, the box plots, so these are the price bounds that we get for the exotic option. This is compared in our paper to the results by Geratowicz and co-authors. Okay, so one last empirical results. Here we have real call options written on the S&P 500 with 10 strikes and 4 maturities. And this is nice because it allows for a direct comparison with the results given in Gupta and Reisinger, where they have exactly the same data set and the same hyperparameters, as they are also considering a Bayesian scheme. Here, the implied volatility bounds are obtained using the posterior min and max. So the shape doesn't correspond to one of standard volatility surfaces. What is the insight here? So the bounds that we get from our scheme are a bit tighter as the bounds obtained in Gupta and Reisinger. Again, they also consider a Bayesian calibration scheme. The plot suggests that the neural SDE adequately learns the surface stemming from empirical call prices. Okay, so conclusion of future research, we consider a comprehensive Bayesian framework, theoretical results, as well as empirical results for neural SDEs. The code is available on GitHub. And yeah, so in possible future work, I would like to maybe extend this to a time series of option data. And I would also be interested in working on neural SDEs or in neural stochastic processes with jumps. Thank you very much for your attention. You can find the paper here.